watch a lot of movies, but when I do watch movies, they tend to be horror movies. Not so much anymore, but I've noticed that they tend to be really hit or miss for people. Like one movie I might find absolutely terrifying might not even faze you, and vice versa. Especially psychological thrillers. I had a friend who knew I was claustrophobic, and he said, you should play, Nauta. I looked into it, I'm like, are you crazy? It's not, I'm claustrophobic. I don't know what that means. I've never even looked at video games like that. I've tried, I haven't gotten to it.
Lost a lot of. I don't know.
Close stuff. I would see if I can break video games. Can't. I went to Halo with a friend. I think it was Halo 3, and you know they have the little cars in the cavern. I somehow got sucked up top. I couldn't get out. I was like, what did you do? You're never allowed to drive again. That's about how video games go for me most of the time.
I don't even play video games. Watch TV or
Me neither.
movie.
I don't have the patience for movies or TV shows. Because my fiance is crazy. And my kids. They'll try to sit down for a movie with me and I'll be getting like 20 minutes in. I'm like, okay, I'm done. I'll fall asleep.
Okay.
One of my friends, it took 4 attempts to get me to sit through Austin Powers.
Wait, what?
The first one. I was the other one. I kept falling asleep. I've seen the beginning of that movie like 4 times. My fiance tried to show me movies and I don't know. I can read, but movies just aren't my preferred media.
I've seen
my classes for this.
And only because
They're like online,
someone
and then
dropped they downloaded.
I think for this day, I have like I was gonna do it at home, but it's like 9 to 10:15, so I'll probably wake up early and go to school to do that right before I have lab and everything.
Cool.
And then my phone's online also, so
Yeah,
I don't have to do anything other than come to school on Tuesdays and Thursdays.
that's pretty sweet. Just making sure you're all signed up. Sweet. Oh my gosh. So happy Thursday. So like I said, we're going to just do some practice problems today. So good day to ask questions about anything, including chapter 7. So we'll just start off with these 2 warm-up problems. So writing the formula for aluminum sulfate octahydrate, and then you can look through these book problems. So just classifying our reactions. I'll give people a few more minutes and then we'll go over them. So what do we get for aluminum sulfate octahydrate? Somebody? Campbell. Yeah. Oh, no, this one, aluminum.
Oh, the formula?
Yeah, did you write that?
Oh, no, I did the.
Oh, okay, so we'll put that down. So skipping over our naming for a second. So A, do we like decomposition? Thumbs up, thumbs down. So yes, right, so one thing becoming 2 things, so that looks good. All right, so Sky, you want to give us? Except, so what's sulfate again? Yeah, so the SO4. So Al2, SO4, and then what do we need? I think you said it 3, right? So 3 still works since sulfate, yeah, -2, so that still works out. So does that look good to everybody? We've got this answer. So of course, right, remembering to balance our cation, our polyatomic, just like we were doing before, and the octa for 8. So that looks good there. All right, so let's continue with these classification ones. So what did B look like? What kind of reaction? So I hear a single replacement. Do we like that? Thumbs up, thumbs down. So I see some nods. So that looks good, right? So you have a metal, then looks like it kicked out this metal. So single replacement or displacement. What about C? What kind of reaction does that look like? So it looks like, so do we hear double replacement? So I see lots of nods for that. So that looks good, right? So again, looks like they're swapping partners. We had sodium and chlorine, and then they swapped to make HCl and sodium sulfate. So double replacement. Excellent. And then our other key is, okay, well, we made solid again and gas, so that's driving our reaction forward. And then this last one, what's this one? So single replacement. Do you like that? Thumbs up, thumbs down? Yeah, so everybody likes it. So single replacement. Right. Questions on this one? And so, of course, right, again, obviously this reaction happened, but I want to point out, now I forgot where I put it. Oh, so right, I want to point out that again, right, it depends on this metal activity series, and the metal has to be higher, and then hydrogen should be right here, by the way. So when we're comparing whether hydrogen can be kicked out or not, so it'd be right here between copper and lead. All right, so see if you can predict the products of these single replacement reactions. So let's start with A. So what did we predict the products to be? So single replacement, that's your hint here. So I hear BaO, so barium oxide, so that would be one of the products I would expect. And then what's the other one then? So H2 gas. Excellent, and that looks balanced, right? So that makes sense. So remember, oxide formations are pretty popular, but then we're also thinking back to our activity series, so barium higher than hydrogen, so it can kick it out, and then giving us H2 gas, of course. Do we do B? What do we get for B there? So I hear iron sulfate. Do we agree with that? And then, so what else is formed? Yeah, H2, right? So that makes sense as well. Iron sulfate, pretty common. So what do we think about C then? Yeah. Yep, so calcium bromide, and then what's our other product? Hydrogen. So that looks good, and then now this one we have to balance. So I'll put our 2 in front of our HBr at least. So that looks good. What about the next one? So lead chloride, so lead 2 chloride, and then what's our other product? And H2 again. So quite a pattern there of hydrogen gas evolution. Questions on those?
Would we on the last one have to write 2 before the HCl or no?
Oh, yeah, sorry, I didn't balance that. Thank you. Other questions, comments? So let's practice an oxidation state 1. And so just try it out and see what you get. Oops, that's my words fly around. And so I will say that this is a case of where we'll see where our oxidation states really are just bookkeeping, electronic bookkeeping. So see if you can figure out what I mean by that. So again, just try to determine your oxidation states of all these elements, and we'll go over everything. Geez, I don't know what happened there. So just in general, when things get like oxygen added to them, that's generally considered that they're oxidized, but just go through it mathematically though. So that's. So let's see where you're at. So let's start with the easy ones. So what do we get for the oxidation state of this O2 here? What is it? I think you kind of said it, Kimmel. So neutral, so 0, right? So elemental form. Okay, so by itself. That's good. I'm going to skip this for now because it looks funky, but we'll address it. Let's look at our products. So what's our oxygen? So again, oxygen is always a good starting place. So now what's oxygen and CO2? Yeah, -2, so each one -2. So what does that make our carbon? +2 or positive? Yeah, so +4. And then so we have hydrogen and oxygen. So oxygen is what again? So -2 still, hydrogen, +1. Okay, so now let's go back to this C3H8. And so we're going to have to base it off of our hydrogens. And so what's hydrogen again? So +1. Okay, so now we can at least determine that hydrogen is neither oxidized nor reduced, right? It was just hanging out the whole time. And so, okay, now we're just focusing on carbon and oxygen. And so now we just have to do this mathematically. And so, right, just take the algebraic approach. So this whole thing has to equal 0. There's 8 of them, so we have to set up, our algebra. So 0 equals 3 times, I'll put carbon for carbon oxidation state, plus, so 1 times 8 or 8. So then, let me just get out my calculator. So then we should get something, so -8 divided by 3. So each carbon has, and you could leave it as -8/3 then, since, right, that gives us a fraction. So each carbon is -8/3 for the oxidation state. And so let's just talk about, well, what does this mean, right? So again, we said that this is just kind of an electronic bookkeeping in some ways. And especially when we're looking at these organic structures and we don't have the picture of it. So later on, we as a class are going to revisit organic structures. We're going to talk about how to determine the oxidation state of each element, but that's a little bit more involved and we have to kind of pick it apart and dissect it. So we're going to save that. I believe it's third quarter when we'll revisit that. So right now, right, we're just taking this simple mathematic approach. We're not trying to dissect a structure and look at each individual carbon. We're just saying as an average, right, it's -8 1/3. So probably some are, -2, some are, whatever. So they all have maybe slightly different oxidation states. Yeah. So -8/3, yeah. All right, so now we have our oxidation states. So who was reduced? So oxygen, right, so it went from 0 to -2, so it gained electrons. So oxygen. We could add to it, right, the other term. It was our oxidizing agent. And so then that means that our carbon must have been oxidized. And okay, right, we see that. So it goes from a negative oxidation state to positive. So oxidation is losing electrons. So that checks out. So carbon, right, we can say carbon was the reducing agent since it supplied the electrons, right? And again, so that makes it oxidized. All right, questions about this one or anything?
So it's the specific atoms that are getting oxidized or reduced.
So oxygen was reduced then, right? Again, just examining your oxidation state. So it went from 0 to -2, so it got more negative. And then carbon, right, we saw was more positive. And then hydrogen, right, we confirmed it didn't do anything, stayed the same. Did that answer?
So when it comes to oxidation and reduction, is it the act of hydrogen bonding to oxygen, or is it the change in the number of electrons that defines whether or not it's oxidized or reduced?
So it's defined by the number of electrons. So like I mentioned, if something adds oxygens, like in this case, right, carbon replace a bunch of hydrogens with oxygens, so that's usually a good indicator that yes, it got oxidized. So adding oxygens usually means oxidation. Adding hydrogens usually means reduction. But again, right, it's all about the math, so you just prove it with the oxidation states.
Can something be oxidized or reduced with other elements?
Sorry?
Can other elements oxidize or reduce compound?
Yeah, so this is just one combustion example. All right, so let's try this one. Actually, we'll go through it together because we didn't talk about how to do this explicitly. And so now we have our usual double displacement reaction. So it says balance our equation and write the corresponding net ionic equation. So we have to go over what that means. And so kind of the trick behind it and what it's trying to show is, really what are the important species. And so again, the way to think about this is, well, if we have silver nitrate and it's aqueous, that means it's just running around in solution. So silver ions and nitrate, okay. And then we have sodium sulfide, again, aqueous in solution. So that's just telling us, again, that it's running around like so. And so what we care about is our precipitate. So again, right, our precipitate is going to drive our reaction forward. So our silver and our sulfide dropping out of solution. And so we want to show this with our net ionic equation. And so you can kind of write it out. So the full way to do it is, again, show everything disassociated. And I need to balance it. So let's see, are we balanced? Now we're balanced. Yeah.
When you say the precipitate drives the reaction forward, what do you mean?
Because again, if you had, so let's draw a different scenario. So I think we had mentioned a similar scenario, but if we had had, oops, let's put in our bucket sodium nitrate and potassium chloride, right, that would just stare at you since there's no combination that's insoluble, right? So you can test them all out. Well, potassium nitrate, that's still soluble. Sodium chloride, still soluble, right? So no matter what, it's just an aqueous solution staring back. Yeah, so it's just clear. So then this one, right, what kind of drives it, and again, that precipitate coming out is, of course, these ions floating around and then meeting and dropping out. So then we're trying to show that with our equation. So now I'm just writing out all our species, again, as ions in solution, just kind of showing what we have in our little bucket. And then writing out our products. And so again, the whole significance of your precipitate is that it stays together now, signified also by our little s. So now it's a solid, it came out. And then plus, so 2 sodiums and 2 nitrates. And so now we can do what's called crossing out your spectator ions. So you're just crossing out what's the same on each side. But again, what you're really doing is crossing out the ions that are just staring at you, right? So again, in our bucket, I don't really care what the sodium and the nitrate are doing. They're just floating around, disassociated. So we can get rid of those. Yeah.
Are they still important to the reaction?
Not really, because we could change the ion, and that's kind of the point of the net ionic equation.
How do you know which ones, like, which ones that you're gonna, cross out? Which
So
ones are the spectator
I
ions?
crossed out whichever ones are the same. So, right, we have 2 sodiums, but they're just whichever ones are involved in the solid, right? Because this is your solid. So I know I need silver, and I know I need sulfide, because we're trying to show those 2 ions are coming together. And then the net ionic is the summary of this. So now rewriting it. So we're saying I have 2 silver ions. And this is where I was saying, like, it doesn't matter. We could swap this out for silver. Now I'm blanking. Probably silver acetate would be soluble, but some sort of ion, some other ion, right? So it doesn't really matter that it's nitrate. It just matters that the silver itself is soluble. And then same thing with the sulfide. So sodium sulfide is a pretty common and cheap source of sulfide, but right, potassium sulfide, barium sulfide, we could swap that out. Although probably barium would be a bad choice because it can make insoluble other things. And then so plus sulfide gives us, right, our silver sulfide. Yeah.
So because, like, when you're doing the net ionic, because you break up the aqueous solutions because they're just floating. Like,
Yeah.
aqueous compounds, you can break them up into their
Yeah.
elements because they're just kind of floating around in there.
Yeah, because that's the whole definition of an aqueous compound is that it disassociates. So yeah, it's just floating around. And then again, the question is, when it meets something, is that insoluble such that it falls out of solution? So that's where we go to the solubility rules, or in this case, right, it told us which one was a solid. 2 front of where? Sorry.
Up at the top, the nitrate.
So yeah, there's a 2 in front of this sodium nitrate to balance it, and then so there should be a 2.
Like when you separated them, it looks like there was a three, like next to the first one that was first. Yeah.
Oh, that's supposed to be a 2. I think it just got drawn funny.
And the spectator ions are the ones that are involved in the
Yeah, so then we can say that everything else, right, all these floating around, so our sodium and our nitrate are both spectator. And so just meaning, right, they were just looking at it, but right, we can just see they're just floating around, hanging out.
And then there's, if we go back up, so at the end product, there's no other charge associated, like, that's the balance charge.
Yeah, because we're just caring about that we put a silver 1+ ion, right? Again, the counter ion doesn't matter. So that's what all we're trying to show. Same thing, right? We're adding sulfide. Counter ion doesn't matter that much as long as it's soluble. All right, so let's try to predict some of these. So let's just start off with A and B, and we'll see how they go. So do we have some thoughts on A, what the insoluble product might be? Yeah.
Copper sulfide.
Yeah, that would be my guess, right? So copper sulfide, so we can look at our solubility rules. So sulfides are generally insoluble. So those group 1 and 2s are the exception, but copper is not on there. So yes, copper sulfide, so that would be our insoluble, so put our little S there. And so now I'm just writing out our spectator ions for completion's sake. So of course, our chlorides are just hanging around. Our sodium is just hanging around, right? We can do the double displacement, see that we would make sodium chloride. So that's soluble. So then now we can just rewrite this. So copper 2 plus sulfide gives us copper 2 sulfide there. So take another minute or so for B.
Is the insoluble compound always the precipitate?
Yeah, so you have to look at the solubility rules, determine which one's insoluble, and yes, that should be the precipitate. So what do we get for our precipitate for B? What do you predict?
Magnesium carbonate.
So magnesium carbonate. So do we all agree with that? So yes, that sounds like a good prediction. And so we could either write out the net, this whole shebang, or we can just kind of quickly recognize, okay, we have magnesium plus our carbonate, right, to give us our magnesium carbonate there. All right, we might as well do C and D for practice. So what do we predict for C? What's the insoluble product?
Barium sulfate.
So barium sulfate, I like it. So sulfates are insoluble, especially with barium. And so again, we can write our net ionic, so we just care about our barium and our equivalent of sulfate. Make barium sulfate. And then did we look at D there? So what do we predict would be the insoluble product from D?
There would be no reaction.
What about mercury chloride though? Hg2Cl.
The mercury bonding with the chloride cancels out the role of most chlorides being soluble.
Yeah, so I would expect mercury chloride to be insoluble. We could double check that. Maybe I'm wrong. Let's see, what are your, yeah, so I would go by your PDF rules. Oops, sorry. I think you have one that's similar to this. So yeah, chlorides, but exceptions are usually silver, mercury, and lead. So Hg2, 2+. So yeah, I would expect that to be our product. And then this one's a little funny, right? So this mercury is kind of like a little dimer. So each mercury is 1, but there are 2 of them. Oops, sorry. So then plus 2 chlorides. Oh, Hg, sorry. There we go. Let's try 2 more examples that I pulled. So see if you can predict the products of this one. And this copper hydroxide plus acetic acid. So what do we predict for calcium nitrate and hydrochloric acid? Yeah.
I'm not sure if this is correct, but I got calcium chloride and hydrogen nitride.
So nitric acid. So what's the problem with that, though? So you're correct that those would be, right, the predicted products. I'm just writing out at least the double displacement to begin with. So what's the problem? Oops, sorry. Help if I wrote that correctly. What do we know about calcium chloride and nitric acid? Yeah, they're both soluble, right? So we could put a little AQ next to both of them. But that just means that, right, the reaction would stare at us, so this would actually be no reaction. So when both of our products are aqueous soluble, then it's just no reaction.
Is there a way to stimulate a reaction if both aqueous?
So not in this case, right? So then you have to kind of add something else to, I'd probably pick something to, get rid of your calcium. So you could add a carbonate and then your calcium would fall out. But. All right, so what about this one? Do we predict the products? So what are the products? Yeah.
What's that symbol?
This is acetate or acetic acid. So I drew acetic acid here. So the formula is C2H123. Yeah, that's acetate. I just have a much easier time remembering it structurally than C2H3OOH or whatever. So then what would the products be? So do your double displacement. What do you predict, your two products? And so don't forget, so I drew it like this, but I should highlight, right, the acidic proton that's going to leave and make acetate. So I'll draw acetate, the salt form. And this is a CH3, just to be clear. So this is acetate, your polyatomic. So then doing the double displacement, what should your two products be? So who would copper pair with? What's the other anion? So there's, you have to treat acetate though, right, as it's polyatomic. And so, right, that's a proton that's going to leave that just makes it acetic acid versus acetate. So then what does that make your product? So it'd be better if we wrote acetic acid so we can really see it as H and then C2H3O COO. Oh, too many C's, sorry, my bad.
Why do you write oxygen twice instead of a subscript?
It depends how people feel. is, so the reason why I wrote it out like this is to indicate that this is a carboxylic acid group. So that's why I bother writing at COOH, so that's what people are trying to show you. Because otherwise, if you're just doing C2H3, O2, you may not as easily recognize that, because then you're like, well, I don't know what that is. But that's why I'm trying to show it to you in all the ways, because students cannot recognize acetate, because it's always in this form or that form or this way. So that's the whole point, is you got to try to recognize it, because nothing is going to be consistent.
So is that common practice to write out the most reactive group with the carboxylic acid?
Again, it depends, just how, whatever you happen to be reading, like whatever bottle. There's no consistency, unfortunately, which is why, again, I'm showing it to you both ways.
What you wrote under acetic acid, you pulled a proton and just separated that outside. Does that mean it'd be C2H2? Or just because you just put the H in front of?
No, this H3 is from here. So you have CH3 on this side. And then this H I'm trying to show is the cation. So that's the acidic proton. But this is, yeah, essentially your cation for our purposes, right? To do our double displacement. And then that leaves acetate as our anion. So now doing the double displacement, that gives us, what are our two products still? So what's copper going to pair with? What's the only?
With acetate?
Yeah, with acetate, right? So it's the other anion. Yep, and then water. So that's the other key in this, right? So it's important that we recognize water, because copper acetate is soluble. So technically, we didn't have our water formation, right? This reaction wouldn't go. So those are two products. And so, right, this is actually a neutralization reaction. So kind of hidden in there. And so water, so, right, this is key. So again, water formation drives the reaction. And so this would be aqueous copper acetate. Any questions on that one? So those two were obviously a little trickier. That was the point, though.
So when we see acetic acid in a situation like this, that hydrogen that's at the tail end of it, that's the proton that can get donated.
Yeah, and that's really like the only action that you're looking at. And that's like kind of, again, what we want to recognize with the organic acids, that it's just that carboxylic acid group, so just this proton that's acidic, right? So we're not trying to look anything else, right? Again, we don't want to get confused by the C2 and the H3 and anything else. We're just focusing on, okay, there's the acetate, then it's paired with our hydrogen, that's our acidic proton, and then obviously giving us the corresponding acid, and then this is the salt, so just seeing that relationship, yeah. All right, so it is break time, quiz time. So I'll probably hand out the quiz, and again, right, you can take your break if you need it. And yeah, and then of course, ask questions. I'll try to hand back your papers. I've been busy grading. I just need to hand you back all your stacks now.
Yeah, like, he has like another tutor that, like, I could be going for an hour.
Yeah.
After that, you should reach out. Okay. I told him I gave you his contact. Thank you. And it's okay, you know, I'm not so used to it.
Yeah, once he started putting the stuff is what